Hi guys, welcome back to the channel. In this video we are going to discuss a concept that is carry look ahead adder. So this is also simply called CLA adder. So this will reduce the propagation delay of the carry. So let's see how it will reduce the carry propagation delay. We already know the full adder circuit diagram. So this is the full adder circuit diagram and the block diagram as well. We already saw the 4-bit parallel adder or ripple carry adder in the previous video. So this is the 4-bit parallel adder. So full adders of 4 full adders are cascaded in such a way that is it will produce all these things. So in the first one, carry 1, carry 2, carry 3, carry 4, it will be much more thing if you are using the 4-bit adder. So to reduce the propagation delay of the carry, we are going to use the ripple carry adder. Instead of that, we are going to use CLA adder, carry look ahead adder. Before seeing CLAs, the propagation delay, how it will reduce the propagation delay. So this is the ripple carry adder, 4-bit ripple carry adder, that you can observe there that every position for first carry for the first sum, for second carry second sum, like that we have found all these sum and carries according to the given things. So we can find any of the thing that we want. So the each full adder, suppose if you take full adder 2, it has to wait for the full adder 1's carry. So likewise if you take full adder 3, it has to wait for the carry for the full adder 2, carry of the full adder 2. So this is the main issue in the 4-bit parallel adder or ripple carry adder. So what if the circuit or a combinational circuit can produce the carries so that it can produce automatically? So you can observe here, so it is very efficient or very faster, you can say faster, so as compared to the ripple carry adder, because carries are generated in the combinational circuit, it can be utilized by the full adder very instantly, and it can produce the sum and carry, means it can produce the sums instantly. We also read that only. So this is a simple format of representing a thing. So this is not the CLA adder, so we are going to, this is the same model that we can represent the CLA adder. So we will be seeing that. You can observe here clearly that marked as the carries also, that is generated directly from the combinational circuit instead of generating from the previous full adders. By this we can reduce the time of producing the output of carries or carry output from the full adder, so the time will be reduced. For the understanding of CLA adder, that is carry look ahead adder, so let's start with the first basic thing in the first full adder, that is full adder. Forgot about all these things. We are going to start from the basic and we are going to understand all these things in the carry look ahead adder. So in the first full adder, we are going to have two things called carry generation and carry propagation. So basically we are looking at the carry. So the name itself suggests it's a carry. So don't look at the sum, let's just look at the carry. So carry should be 1. Then only it can propagate. If carry is 0, it cannot propagate. So carry is 1. So basically carry will be 1 when any of the one input is 1 or both the inputs is 1. So we are going to have any of the inputs as 1 in the first case. So if we observe that A dot B will be 1 in the first situation. That A dot B is also known as the carry generation, because carry is generated with the A dot B. So if you observe, if anything that A XOR B dot C, if that is 0 also no problem, because that is OR gate. So that the single one, that is 1 plus 0 is 1 only. So with the help of A dot B only we are generating the carry. So that is known as carry generation. So now let's understand what is meant by carry propagation. So if you observe clearly, we have already saw A dot B is equals to 1. So if A dot B is 0, assume that. So then A XOR B dot C, if that is 1, then the output would be whole output, carry output would be 1. So if you observe, if you take C as 1, so because we need 1 in that output, so that is AND gate. So both of the inputs would be 1, then only output would be 1. So carry, if you take 1, so the final thing, that is A XOR B should be 1. When that is 1, when both the A and B are opposite, so that is known as carry propagation, because if A XOR B is 1, then whole output of the carry would be 1. So this carry A XOR B replicates the whole output, so this is known as carry propagation, the A XOR B. So you can consider that P is equals to A XOR B. P is also known as the carry propagation. Now it's time to construct the 4-bit CLA, that is 4-bit carry look ahead adder. So for that we are going to look at first full adder. So if you observe the first full adder, that is we are passing A naught B naught. So in the position that is P naught, that we are going to assume A XOR B, A naught XOR B naught. And if you observe down also, Z naught is equals to A naught into B naught. because we already observed that G is equal to AB, B is equal to A XOR B. So in that situation, we are going to replace that A0 B0 with the Z0 and A0 XOR B0 with P0. So in places of outputs also we can observe that is P0 XOR C0 for a carry, that is C1, that is P0 into C0 plus A0 into B0. Finally, if you consider the C1 output, that is Z0 plus P0 C0, you can observe, you can understand from the circuit diagram itself simply. I already said we are going to construct 4-bit CLA. For that, we already saw the first full adder. So the first full adder's carry will be the one of the input of the second full adder. So let's also see the second full adder. So if you observe, this is the second full adder. The final carry that we are seeing, that is C2. So our aim is to reduce the propagation delay of carry 2. So for that, we are also going to observe the carry 2. So C2 is equals to G1 plus P1 into C1. So I hope you know the meaning of Z1 into P1. So Z1 is equals to A1 into B1 and P1 is equals to A1 XOR B1. So from this that we are going to replace the C1 with the G0 plus P0 into C0, because we already know the meaning of C1. We already saw in the first full adder. So after replacing the C1, multiply that. So we are going to obtain the C2 as final output in the second full adder. For the construction of 4-bit CLA, we are going to have the third full adder. We already saw 2 full adders. So in this third full adder, we are going to observe at the carry, that is C3. So C3 output would be G2 plus P2 into C2. So we already know G2 is equal to A2 into B2 and P2 is equal to A2 XOR B2, because we are passing A2, B2 as inputs, and we are taking third input as the previous carry, that is C2, that is carry from the previous second adder. We already saw what is meant by C2, so replace C2 with the G1 plus P1 C1. So the C3 equation becomes like that. So in that we have that the sum to PV2 P1 should be distributed. So after distributing, the C3 output equation would be like that. So this is the final output of C3. The fourth full adder in the construction of 4-bit CLA carry lookup adder, we are going to have C3, C2, C1, because if you observe the C4, that is Z3 plus P3 into C3, because we are going to pass the third input C3 from the previous carry, so that is C3, and we are going to pass A3, B3 because these are the inputs. So if you observe, we already know the C3, so replace C3 with the G2 plus P2 into C2. So after multiplying with the P3, we already know the C2, so replace the C2 with the G1 plus P1 into C1. So we already know the C1 also, so replace with the G0 plus P0 into C0. So after multiplying all the terms inside that, we are going to have the C4 output as the 5 terms sum. You can observe there. With these 4 carries, we can do, or we can produce the circuit diagram for the 4-bit CLA, 4-bit carry lookup ahead adder. These are the 4 carry output expressions, that is C1, C2, C3, C4. So you can also observe what is meant by Pn and Gn. Gn means the dot product and Pn means the XOR operation. Actually, we are going to build the circuit diagram now. So for that, if you observe, we are going to see each and individual carry circuit diagram, so that after that we are going to merge all the circuit diagrams of these 4 carries. So I have drawn the 9 lines. So that is C0, G0, G1, G2, G3, P0, P1, P2, P3, because if you observe all these C1, C2, C3, C4 equations, we are going to have total 9 variables. That is already I have drawn the line equations, because we are going to connect directly with the help of dot product, means the OR gates and AND gates, so that we can produce the circuit diagram very easily. So if you first look at the C1, that is carry 1 of the first full adder, that is Z0 plus P0 C0. If you observe there, so we have one plus operator, means that is OR gate. We have one AND gate, that is P0 into C0. So I am taking one input from C0 line and one input from P0 line. I am doing the AND operation, and the second, the input of the OR gate will be taken from Z0. I hope you can relate the C1 expression with the circuit diagram as well. I have the C4 expression as very big, so that I am taking 9 lines at a time. So the OR operation output would be the final output expression. The next step, we are going to see the second full adder carry, that is C2, that is Z1 plus P0 G0 plus P1 P0 C0. So for this output expression, I hope you also know we have 2 OR gates. So instead of representing two OR gates, I am representing in a single OR gate, that is 3 input OR gate, and we are going to have two product terms, that is P0 G0, P1 P0 C0. For that we need to have one 3 input AND gate. So I am taking 3 inputs from the lines, that is P0 P1 C0. So I am taking third input of OR gate, that is G1. So I hope you can relate the C2 expression of output expression and you can formulate the circuit diagram as well. It is very simple, I think. So the next step we are going to follow is the C3. So we have C3 output expression. So for the third full adder in the CLA, we are going to have the carry like this. The circuit diagram you can relate with the second one also, the second carry C2 also, because in this we have three product terms, that is P2 G1, P2 P1 G0, P2 P1 P0 C0. For this we are going to have the 2 input AND gate, 3 input AND gate, and 4 input AND gate, and one 4 input OR gate. So instead of representing directly with the help of 4 input OR gate, I am representing like this in this fashion. So it is valid and that is also valid. We can represent at a time 4 inputs and one OR gate. So similarly in the previous one we are going to map all the things with the corresponding lines, that is input lines shown over the above. The final main thing in the formation of 4-bit CLA, that is C for output expression, that is carry of the fourth output expression, that is you can observe there. You can also have in this 2 input AND, 3 input AND, 4 input AND, and 5 input AND, because the output expressions are like that. So you can also form like this and you can do like that. I hope you can understand or you can relate that with the previous one. So actually this is my whole circuit diagram, that the C1 should be come at the bottom of the thing and the C2 should become above, C3 above, C4 above. But sorry for the inconvenience, the circuit diagram, but according to the things we have to adjust all the things in the same line. So as space is not adjusted according to Lee, so I have congested all the circuit diagrams. So but you can relate with in the paper very simply. You can map all the lines in that. In the things that we have already saw, C1, C2, C3, C4 individually, you have to place the same things here also, C1, C2, C3, C4 according to in a simple straight line manner. But I have represented in a wrong manner because the space is not adjusted clearly here. But the format is same. You have to adjust all the things in a hierarchical manner. The construction of 4-bit CLA is just started now. So up to now what we have saw is just the carry or just the carry. So we have took the input lines as that is from C0, P0, G0, P1. So these are the things that we did not saw. So in the inside the full circuit, that is CLA. So that is the simple thing that I have represented all the circuit that we have saw up to now. So this is the actual circuit diagram of 4-bit CLA. So because we are simply passing the P0 and G0 in the CLA, so after that we are going to obtain C1. So what is meant by P0 and G0? So P0 means A0 into B0 and G0 means A0 XOR B0. We already saw the definitions of G0 means G and P, that is carry generation and carry propagation in this lecture only. So just start all A0 B0, A1 B1, A2 B2 and A3 B3 in the CLA. So CLA means this block represents the thing that we have solved up to now. That is, it will produce the carries. So after producing carry, that is C1, C2, C3, C4, it will produce. To obtain the sum, we need to take the first output would be directly produced with the P0. P0 means A0 XOR B0. Sorry, P0 means A0 B0. So you can pass directly to the XOR gate and you will produce the sum out, the first sum. In the second one, you need to produce the carry C1. So these carries are produced with the help of the thing that we have saw up to now, that big circuit. So you can pass the C1 to the XOR gate. You are going to output the X1 and C2, C3, C4. So these carries are produced with the help of the big circuit that we have saw up to now. So you are going to produce the sums. So this is the CLA block, or you can produce the 4-bit CLA in the block circuit diagram. This is very simple diagram. You can relate. This circuit diagram you can observe clearly that is in the same line. If any circuit or any logic gate present in the same line, that is considered as a single gate. So if you observe from passing, if you are passing A0 B0, it is going to that, it is one gate delay, it is known as. In the block diagram of CLA, that big circuit we have saw now only, that is inside we have two logic gates only, that is AND gate and OR gate. So that is known as two gates delay. As I already said, so C1, C2, C3, C4 will be produced by the big circuit that we have saw already before. So these are present in the same line, so that is 1 gate delay. So this whole block, CLA block, will be in 2 gate delays, because in that we are going to see now. So if you want sum, so if you want carry, we are going to cross 3 gate delays. If you want sum, we are going to cross the another gate delay, that is XOR gate. So all the 4 present in the same line, so we can take it as one single gate delay. I will explain now how in between the CLA we will be going to have 2 gate delays. See this clearly, this is the diagram that I am speaking about. So C1, C2, C3, C4 will be produced in the middle block, that is CLA block. So this whole circuit will be present inside that block. I hope you are understanding. So the lines also, the 8 lines also that I have drawn, in this I have represented in a horizontal manner, but in the block diagram I am representing in a vertical manner. The red, blue, black lines, those are nothing but what? C0, G0, P0, those things that are representing in a horizontal manner in the block diagram of 4-bit CLA. If you observe, all the AND gates will be one gate, and all the OR gates will be another gate. So we can simply say this has 2 logic gate delays. Or you can also observe here clearly, we are passing the sum of the operators like G0, P0, something we are passing, but we are getting outputs as carries only. So with this help of whole circuit diagram, we can produce only carries. That is the reason that we have drawn this. But this is not the full circuit diagram. So the block diagram that we have saw now, that is the full diagram that I will show now. This is the thing. This is the full circuit diagram of 4-bit CLA. If you observe, in the horizontal manner, inside we are passing C0, P0, G0. So these are only in the vertical fashion, or in the horizontal fashion we are passing. Same way we can represent in any of the manner. These are only things that we are passing in the for the carry or input. Now only we saw that things in the blue, black and red line. The red line is C0, but here we are simply representing C0, and blue lines are P0, P1, P2, P3, and the black lines are G0, G1, G2, G3. After passing some operators, we are getting output as C1, C2, C3, C4. I hope you can relate. In between, I simply represented as block of a block operator, and you can see that 2 gate delays. So you can observe clearly that is carry delayed would be 3 gate delays, because that whole thing, that is we are passing in a whole thing, we are getting after 1 gate delay, and again you are passing 2 gate delays. So finally we are getting after 3 gate delays, we are getting the carry. So if you want the sum that is produced after another 1 logic gate delay, that is sum will be delayed after 4 logic gate delays. I hope you can understand this thing. Okay, up to now we have understood the gate delays, how many gate delays for the sum and carry, final sum and final carry for the 4-bit CLA carry look ahead adder. So if you want to compare with the ripple carry adder or the parallel adder, then only we can understand it is more better than the parallel adder, CLA is more better than the parallel adder or not. So that is the reason we are using CLA. So that let's first understand the logic gate delay for the parallel adder, so that for 4-bit parallel adder, so that we can understand why this is more and why that is very less as compared to that. So this is the thing that we have already saw in the previous video. You can observe the final sum S3 can be produced at 2 XOR plus 6 TP, and the final carry C4 can be produced after T XOR plus 8 TP. First, let's observe the carry C4, the final carry of the ripple carry adder or parallel adder. So that is simply represented as the formula, we can say that is T XOR plus 2n TP. So n is nothing but the number of full adder blocks. So that is the formula. Here number of full adders are 4. So simply represent n is equals to 4. So that becomes T XOR plus 8 TP. That is time delay or propagation delay for the carry 4. So if XOR is equals to TP, the propagation delay of XOR on the TP means the AND gate propagation delay and the OR gate propagation delay. Both are same. The AND gate propagation delay is known as TP, and the OR gate propagation delay is also known as TP. If both are equal, XOR propagation delay and propagation delay of AND gate, so then the output would be T XOR plus 2 and TP. So in this case n is 4, so replace the n with the 4, so you are going to have the 9 means the 9 as output. 9 gates delay in the parallel adder, 4-bit parallel adder, we can say simply. But in the 4-bit CLA, we just had 3 gate delay for the carry and 4 gate delay for the sum. So for the more clarity, this is the comparison between 4-bit parallel adder and 4-bit carry look ahead adder or CLA. So if you observe, we had a formula for the 4-bit parallel adder, that is T XOR plus 2 and TP. So if XOR is equals to TP, so you are going to take out the TP common, so that you can get 2n plus 1 TP. So n is equals to 4. For the 4 bit we are checking, that is 9 gate delays. So carry would be produced after 9 gate delays for a 4 bit parallel adder. So if we already saw up to now the logic diagram and the circuit diagram for the 4 bit CLA. So from the scratch to up to main thing, we have already described the circuit diagram for the CLA, 4 bit CLA. So if you observe, that is 3 gate delays. So you can see 3 gate delays is very less time delay. So we can consider it is best 4 bit CLA. So next thing we are going to see is 16-bit parallel adder versus 16-bit carry look ahead adder, that is CLA. So if you observe 16-bit, so in the formula, that is T XOR plus 2 NTP, n is equals to 16. Put that, so you are going to obtain 33 logic gate delays. For the carry it will take 33 logic gate delays, and for the sum 34 logic gate delays. I hope you can understand this. That is 16-bit parallel adder. So in the same fashion, you are going to observe, or you are going to formulate with the help of 16-bit CLA, you are going to just have 12-bit gate delays, and for the sum, that is 13-bit gate delays. So if you want the circuit diagram also, so let's see that 16-bit CLA circuit diagram, and how the carry delay is only just 12 gate delays, and how the sum delay is just 13 gate delays. So we will see that, but before that you can observe where the carry is 33 gate delays. It is very huge delay, and if you observe in the 16-bit CLA, it is less delay as compared to the 16-bit parallel adder. So in this also, the fast and efficiency of 16-bit CLA is very more as compared to parallel adder. So the CLA will work faster, that we have understood, but the main drawback or the limitation of the CLA is, it's not the limitation, but for making of CLA it needs much more costly. It is very more costly and very much complex to make that circuits, because for the making of just the carries, we are used many more things. We have used 5 input AND gate, 5 input OR gate, so that many things we are going to use in that formation of just for carries. For the sum and for the propagation, that is P0, G0, C0, and these many things we are going to generate with the help of XOR and AND gate. So this also requires much more complexity. So we can say the complexity and cost of making the circuits are very more compared to high as compared to parallel adder, but the efficiency and the fast will be, this one will be high. So I already said we are going to discuss the circuit diagram of the 16-bit carry look ahead adder, that is CLA. So we all understood that 12 for the carry, 13 for the sum. So let's understand with the help of the circuit diagram as well. So we have already saw the 4-bit CLA, that is in the block diagram we have already saw the 4-bit CLA. So in this 16-bit CLA we are going to have cascaded things of 4 CLA blocks, that is CLA 0, CLA 1, CLA 2, CLA 3. In each CLA block we are going to pass the from 4 inputs, that is in the first one, if you observe, A0 to A3 and B0 to B3, and the carry you have to pass C0, and the sum expressions you are going to obtain from S0 to S3, and you are going to finally obtain the carry as the C4. You are going to pass the C4 to the next CLA. So this whole thing is the first representation of 16-bit CLA. In the 16-bit CLA we have two block diagram representations or 2 circuit diagram representations. So this is the first diagram. In this you can see the C4 carry is passing to the next one, means the next CLA block. So as we already observed, or we know that for the CLA block the carry will be produced after 3 logic gate delays. So in the same fashion we are going to already completed 3 logic gate delays in the C4. For the C8 we are going to complete another 3 logic gate delays, that is the 6th position. In the same fashion after the CLA2, that is 9 logic gate delays, and finally the C16, the carry of C16, the propagation delay of C16 will be produced after 12 logic gate delays. So I hope you are understanding the logic gate delay for the carry will be produced after 12 logic gate delays. So we have already see this thing in the comparison of the 16-bit CLA versus 16-bit parallel adder. So we will see for the sum also now. You can read the statement also down, that is 16-bit adder, the 4-bit CLA propagation delay carry would be 12 logic gate delays. Using this, each cascaded of 4-bit logic gate delays of CLA. Now we are going to see in the first one only, we are going to see for the sum. The last S15, the logic delay or the number of gates required to be obtained the S15 output, the last sum output. So we already saw the carry, that is 12 logic gate delays. For the carry, so if you observe, we are having the C12 as 9 logic gate delays. So 9 plus 4, because for the producing of sum we need 4 logic gate delays. So previous carry plus the sum output would be producing the final output for the S15 sum. So the 9 plus 15, the previous carry plus the current producing sum, that is 4, 13. So we can say that for the 16-bit adder, the 16-bit CLA adder will require 13 logic gate delays for the production of sum, or 13 logic gate delay for the sum. I hope you can understood the first representation of 4-bit to 16-bit CLA adder. So this is the second representation or second circuit diagram representation of the 16-bit carry look ahead adder CLA. So because why we need this? Already we have one representation, then why we need for the 16-bit the second representation? Because this is more efficient than compared to the previous one. Because if you observe, go back and observe the previous one, we have discussed that the previous carry is delayed to the also passed to the second CLA. So that is the main logic or delay. We are using the CLA for the reduction of time delay or to reduce the propagation delay. Again we are going to pass the delay for the next or the carry to the next CLA. So it will produce some delay. So for the small rectification also we are going to have another logic block, that is CLA block. So you can observe there. So you can see that we are again going to use another CLA block. So we are going to pass the carry from the each CLA block to the 4-bit CLA block. So you can observe we are going to have the final output sum from S3 to 0, S0 to S3, and finally we are going to have S12 to S15. We are going to have some outputs, and we are going to pass from A0 to A15 and B0 to B15 also. But in this this is efficient because all the inputs and the carries are produced at a time with the help of everything is produced with the help of carry look at adder. So this is the second representation of 16-bit CLA. It is more efficient than the previous one, because in the previous one also we are passing the carry to second one as the in ripple carry adder. But each block level means each CLA level it is reduced time level. But here each level and each carry it is very less time. It will taking less time for the propagation delays. So it is more important, very important and useful also. I hope you understood the logic circuit diagram and the block diagram of the CLA carry look ahead adder. So thanks for watching up to now.